We have a midterm next week. I'm going to be hosting a live tutorial Sunday night, and I think Terry is going to be doing one as well, probably sometime Saturday. And I don't know what time Saturday, but those will be recorded and posted as well, so you can see those after the fact. I put up a few other things on YouTube. I posted the solutions to the previous midterm, like a video solutions thing. I also posted a video solutions to the 2017 midterm 2. So the 2017 midterm 2 will be probably most similar to this course. It seems like the midterm 2 started in chapter 5, covered 6 and 7, and then did a little bit of 8. So there's a little bit on both ends of that midterm that are not going to be on this one. This one is just 6 and 7. Other than that, I don't really have anything too new to tell you about the midterm. It's got exact same format as last time, more or less. I mean, the written part, slightly different breakdown like that, but moreover, like same length, that kind of stuff, same grade scope. So all the stuff that you've done already for the first midterm be the same. Midterm is on Tuesday, right? Yes, I believe that's correct. 24th, 23rd, 24th, something like that. If you are registered with accessibility services and are going to get extra time, there was people in this situation last time. Just please send me a reminder email to make sure that I have that correctly set up for you. And that's it. We're going to have 2 writes again, early write, late write. The early write is going to be timed so that you can do it at the library, because I believe the library closes at 7. And the library is actually a great spot to write the exam, especially if you want to print the written part out before you scan it. And if you want to be someplace where you're sure you're going to have reliable internet. So yeah, that's where we're at. So what we've covered so far in Unit 7, it's about alkenes. We learned about EZ. We learned about relative stability of alkenes. We learned how to make alkenes from alcohols. And so we said that alcohols, if you want to do elimination, you can't just do elimination straight on an alcohol because the OH group is too bad of a leaving group. If you want to make OH leave, you have to react it with a strong acid first to protonate the alcohol. That turns it into a good leaving group, and then you can do elimination. So we talked about using concentrated sulfuric acid, talked about concentrated phosphoric acid. Both of those are good choices to do elimination on alcohols. We're going to look at a few other acids today, and we're going to be looking at HX acids. So HX acids are HF, HCl, HBr, and HI. Now these are all strong, well, HF is not a strong acid, but all the other ones are strong acids. And what we know is that if you take an alcohol and react it with one of these acids instead of H2SO4 or H3PO4, what happens is instead of dehydration, instead of making an alkene, you get instead substitution. So you can see in this example, we have, in this case, a secondary alcohol reacting with HBr, and it replaces the OH for HBr. So we want to look a little bit into this reaction. This is why it's sort of a separate topic that we're bringing in. It's reaction of alcohols, so it's closely related to what we just looked at with dehydration, but it's not making alkenes, so it doesn't kind of fit the overall theme of Unit 7, which is making alkenes. So what we know is that the strongest acids are most reactive, and HF is the least reactive. In fact, HF does not do this reaction essentially at all. So I think like there's a cutoff here where HCl, HBr, HI are all reactive, HF is not. This is what it means. Like, this is what I mean when I say the reaction is faster. If you take an alcohol and react it with HI, the reaction might take just a couple of minutes. Room temperature, you get very high yields. If you then use a less strong acid, what happens? The reaction takes more time, or it might take a higher temperature, or it might produce a lower yield, or it might do all 3. So practically, when I say a reaction is slower, means under the same conditions, you're going to get a lower yield, or you're going to have to heat it up or do something to speed that reaction up. Some cases it doesn't matter. Some cases it might take 10 seconds and the slow one is 40 seconds. Either way, that's a fast reaction. Another thing that we notice is the reactivity of alcohols mirrors the reactivity we saw for elimination with H2SO4. The fastest ones are tertiary, secondary is slower, primary slower again, and least reactive is methanol. Okay. So this is what happens. Let's cut to the chase. We have our strong acid. Anytime you have a reaction where you have a strong acid as one of the starting materials, almost always your first step is going to be a proton transfer. Same thing if you have a strong base. Strong bases, often the first step is removal of a hydrogen. Okay, so let's throw in HCl with this tertiary alcohol. We have a strong acid and we have an alcohol. The first step is going to be a proton transfer. Just the same first step you would have if it was sulfuric acid. So it looks like this. You have your alcohol, picks up H plus from HCl. The HCl bond breaks, the pair of electrons goes to the chlorine to make chloride. Chloride has 4 lone pairs around it. And you make an oxonium ion. What do you think this oxonium ion might do? It's a great leaving group. If it leaves, it can make a great carbocation. Well, not great. I mean, carbocation, calling them great is a relative thing, but it can make a tertiary carbocation, which is pretty good. So what's likely to happen in this case next is loss of water, loss of your leaving group. First step, proton transfer. Second step, loss of the leaving group to make a tertiary carbocation. That step's not too bad in this case. This looks a lot like the same reaction of the same alcohol with sulfuric acid. In fact, these steps are identical. Proton transfer, loss of leaving group to make a carbocation. The reaction is first order because the rate determining step is making the carbocation. So it's going to be a mechanism with a 1 at the end. And this carbocation will be an intermediate. So what next? Well, the other half of the acid was chloride. We made a chloride in the first step. We learned back in the previous chapter that chloride is a good nucleophile. Terrible base, but great nucleophile. And carbocations love to react with nucleophiles. So that chloride that we produced in the first step can just come and pop on. And this is the reaction. And you make an alkyl chloride. This reaction is very fast, very downhill in energy because you are converting the carbocation to something stable. And you have a nice, small, stable molecule. So this reaction, that's kind of it. It's pretty straightforward. This is a substitution. Unimolecular, because you're making a carbocation. This is just an SN1. Exactly the same as the SN1 from the previous chapter, except for the alcohol, you have to protonate it first, make it a good leaving group. But once you've done that, exact same steps as you would have seen for alkyl halides. So alcohols can do SN1, it can do E1 or E2, but you need a strong acid to make it happen. This is the overall 3 steps just shown in a row. Proton transfer is the first step, which is fast. This is the rate determining step because it makes a carbocation, and the carbocation can quickly react with the chloride from step 1. This does not happen with sulfuric acid because sulfuric acid doesn't have a strong nucleophile as the other half. If sulfuric acid protonated, then what you would get is O, S, OH. And that's a really poor nucleophile because it's resonance stabilized. That has 2 other resonance forms. That negative charge is spread out all over the molecule. And for that reason, this molecule is not really, it's stable. It's not reactive. It's not going to attack. So that's it. 3 steps. Before, our SN1 was 2 steps. Now it's 3 because we have to protonate the alcohol first. 2-propanol, same thing. we're going to take the secondary alcohol in this case, react it with some molecule HX, which is HCl, HBr, HI, not HF because it's not a strong enough acid. And you proton transfer to make the oxonium, lose the leaving group, which is water, to make a secondary carbocation, nucleophile attacks, and you get your secondary alkyl halide. So on this midterm, you're going to be asked to draw mechanisms. It's one of the long answer questions. And when I ask you for a mechanism and I say show all the steps, show all the intermediates, show all the lone pairs, show all the curly arrows, this is what I want to see. I want to see all these steps, everything you see on the screen here. You don't have to label anything unless I ask you to label it. You typically don't have to draw the inorganic products. If you're using sulfuric acid and it makes bisulfate as an anion, you don't have to draw that stuff. Or if you do an elimination and water leaves, you don't have to, like I don't need a whole bunch of stuff at the end, just the organic product. Don't merge two steps into one. So what I see sometimes is people will do kind of two steps together. They'll have all the arrows in one space, and it'll show like something attacking and something leaving at the same time. Make sure every step that happens is a distinct part of this process. Great. Potential energy diagram for the substitution reaction looks a lot like elimination. In fact, the first two steps are the same as elimination. The only difference is once the carbocation is formed, does the nucleophile attack to make substitution, or does some base pull off a hydrogen to make elimination? And we'll talk about why that is. We're going to talk about how you can look at the starting conditions to determine if it's elimination or substitution. It's actually very straightforward. We did this already for the alkyl halides. It's way easier for the alcohols. A lot less chance of different things happening. Yeah, activation energy is small for the first step, large for the carbocation formation step, which makes it slow, and small for the nucleophilic attack step. So this is the rate determining step, as we mentioned, formation of a carbocation. So that's why tertiary alcohols react more quickly than secondary alcohols. Because the slow step is making the carbocation, it's easier to make the tertiary carbocation than the secondary, so the tertiary alcohols react faster than the secondary alcohols. Cool? Great. Now, one thing we talked about last class, which I'm sure everyone loved to hear about, was the rearrangements, right? Rearrangements can happen anytime you have a mechanism where there is a carbocation intermediate. SN1 has a carbocation intermediate. Therefore, we need to be on the lookout for rearrangements here as well. So in this first example, we have an alcohol, gets protonated by HBr, loses the leaving group, and it makes this carbocation here that's secondary. Secondary carbocations are the ones you have to watch out for. If the carbocation was tertiary, you can forget about it. They're not going to rearrange. Generally speaking, tertiary won't rearrange because it's already as stable as it can be. It's already tertiary. Secondaries, though, will rearrange if that can make them tertiary. So this carbocation here can do an alkyl shift. We looked at hydride shifts and alkyl shifts. This is where you take either an alkyl group or a hydrogen from a beta carbon, slide it over one spot, and the cation goes to where the group that shifted over came from. So in this case, you can convert by this rearrangement from a secondary to a tertiary. Once you have the tertiary, then the nucleophile attacks, and you get your product like this. The other thing is this is an SN1. SN1 can give you more than one stereoisomer, right? So that bromine can attack the front or the back carbocation. So the one I drew is just one of the possible products. Yes?
So why can't the bromine attack the
It could, but it doesn't live long enough. The secondary carbocation it's hot, right? It's not very stable. It wants to go down in energy, and it will do that fast. It'll do that before a nucleophile can get there. That's not to say, like, yeah, okay, there might be a little bit of product with the bromine attacking, but if a carbocation can rearrange, it will rearrange quickly, and that will be the major product. So you're right, the bromine could attack the carbocation before it rearranges, and that might be 6% of your product yield or something like that. But in this case, yeah. So this one is a chiral molecule. It'll have an enantiomer. Or the bromine could have also attacked from the other side. You could have had this plus an enantiomer. So this reaction can produce 4 different possible products. All right. Primary alcohols won't do this. Okay. Why? Why wouldn't a primary carbocation do SN or primary alcohol do SN1? It's because primary you can't make a primary carbocation. So primary alcohols can't do mechanisms that involve carbocations. Same reason from chapter 6, primary alkyl halides can't do reactions that make primary carbocations either. So this reaction is no good. You can't protonate the alcohol and then have it just leave and make this primary carbocation. That's not stable. But they still react, so there's a mechanism for these ones as well. It's not E1, it's not E2, it's not SN1. So what do you think it is? SN2, very good. All right, so this is what happens for primary alcohols is you protonate the alcohol with HCl, you make the oxonium ion, just like before. This is fast. Then the nucleophile just attacks, knocks off the leaving group. This is a straightforward, textbook, run-of-the-mill SN2 reaction. Nucleophile attacks, knocks out the leaving group, and this is what happens for primaries. You would get inversion, but primaries can't be chiral centers anyway, so we don't even really have to worry about the fact that this is an inversion, because it only happens for primaries. Secondary and tertiary always do SN1 because they can make carbocations that are stable. This is the slow step. This is the rate determining step. The proton transfer step is the fast step. This has the same transition state we saw in Unit 6. This is the same inversion we saw in Chapter 6. Everything about this reaction is exactly the same as what we saw in Chapter 6, except you have to protonate the alcohol first before it will act as a leaving group. So this is funny, like it's hard and easy at the same time because it has a lot of similarities with what we learned already in the previous unit, which makes it easier to learn. It's not something completely new or different. But on the same hand, on the other hand, same hand, yeah. On the other hand, it's almost the same, but just slightly different. So you have to keep track what makes it different. And what makes it different is you need to activate the OH by protonating it first before it'll leave. All right, this is the potential energy diagram for this. Quick step, which is the proton transfer. Slow step, which is the SN2. Great. So what I want to do is break down for you under what conditions. Remember we had that chart for alkyl halides. One is at SN1, one is at E1, all that kind of stuff. It was kind of a lot to take from that. Like there was a lot of different possibilities and options. This is going to be straightforward. You're going to have methyl, primary, secondary, tertiary alcohol. No, I'm going to go like this. Make a nice box. We're going to have sulfuric acid or phosphoric acid, and we're going to have HX, where X is a halogen. Not just any halogen, one of those three. Tertiary and secondary can make carbocations, so the E1 with phosphoric acid or sulfuric acid, SN1 with HX. So think of the right half here as the carbocation mechanisms. Secondary and tertiary carbocations are possible, so that's what happens. Not possible for the other ones, and so for HX, we have SN2, and for these ones, we have E2 and X. You can't do elimination on a methyl alcohol. So this is a lot more straightforward, isn't it? If it's HX, it's all going to be substitution. If it's sulfuric acid, it's all elimination. If it's secondary or tertiary, it'll be a carbocation variant. If it's not, then it'll be the concerted variant, going with the 2, E2, SN2. Awesome. Cool. So this isn't too bad. What makes this a lot more bearable as well is seeing examples, which that's my plan for Monday, is to spend as much time doing examples as possible. Same with the tutorials, right? We'll get lots of examples in. And there's not a whole lot going to happen in these tutorials except examples of these drawing reactions, drawing mechanisms, drawing products, applying the knowledge that we learned so far in these units. Okay, so we are quite a bit through this unit already. Look how much we've done, everything we've learned. We did Zaitsev's rule. We did methyl shifts. This is what we got to. We did right here. We did rearrangements at the end of last class, and we looked at this example. We looked at the hydride shifts as well. This example. Here's one more example of a kind of a complicated rearrangement. This is an alkyl shift. So this is what happens. You have this alcohol, and you can see this sort of odd structure where we have two rings that are joined at a single carbon. We're going to react it with sulfuric acid, which is going to protonate the alcohol. Once it's protonated, it can leave to make a secondary carbocation. Secondaries are the ones we look for rearrangements. And so we look at the beta positions, and we look for alkyl groups or hydrogens that if we switch them over, kind of trade places with the cation, we could make a tertiary carbocation. A secondary won't rearrange to a different secondary, and a tertiary won't rearrange at all because it's already stable. But in this example, we have our secondary carbocation. This carbon is a beta, and this one's a beta. What can happen is you can shift over that alkyl group cation, put the cation where the group shifted over from to make this. That's a tertiary carbocation, and then it can undergo elimination, sulfuric acid, to make the various products here. This one being major, why? Anyone tell me why that one is the major alkene product and not the other two? How do we tell which is major? Very good. This one is tetra, substituted. These ones are both tri, which is okay, but tetra is better. The most stable one is going to be the major product here. So we're going to look more examples of these on Monday. We're going to go through all the gory details of these alkyl shifts. These are probably the most complicated thing in the whole unit so far. So I guess to summarize with carbocations, there's sort of three things that they can do. They can react with nucleophiles with SN1 reactions. They can lose a beta hydrogen, which is an E1 reaction, or they can rearrange to make a more stable carbocation. And that more stable carbocation will then do one or two. So there's a lot of things that we can expect of our carbocations. Who knew? Before we started this course, every carbon you ever knew had a full octet. Never had a charge, kind of boring, didn't do too much. Yeah, we can get carbons to do a lot of things, especially if you force them to not have a full octet. We're going to jump back and look in a little more detail, apply some of these new things we've learned, and maybe a few other new things to the E2 reactions that we looked at back in Unit 6. Remember in Unit 6, we had alkyl halides, and we would use alkoxides, either a bulky alkoxide or a small alkoxide, and they would do E2 reactions, right? So if you have chloride and you have a hydrogen that's beta, and you have a small alkoxide like ethoxide, you can do an elimination. Okay. We're going to look at that reaction because remember we learned Zaitse's rule for the alcohol dehydrations, which said that if you can form more than one possible product, the major product is going to be the one that's more stable. We looked at that one when we went to Unit 6, we didn't consider that possibility. And if you look at all the examples from Unit 6, all the beta carbons were the same in all the examples. Didn't matter where you took it from, it all gave the same product. We know that's not obviously realistic, that you can in many cases have several possible alkene products. And so you see in this example, we have a tertiary alkyl halide, small alkoxide, which will do E2, but we have 3 beta carbons, 2 types. We have the methyl type, and we have the CH2. And if you remove it from a methyl, you get this one. If you remove it from the CH2, you get this one. And the major product in this case is the tertiary, which follows Zaitse's rule. It's more stable. The more substituted alkene is going to be the major product. So we would say this is regioselective. It's also stereoselective. If you have an example like this, it can produce either the trans or the cis alkene. Trans is more stable. Trans is the major product. So it's stereoselective as well, where you can make more than one stereoisomer. One of them is formed in greater amounts. Great. Here's another weird example. This is a big ring. How many carbons are in this ring? Kind of weird how it kind of folds in on itself a little bit. This has 10 carbons. This is a bromocyclodecane. And you can see rather than try to draw it like, something like that, we draw it sort of folded in. It makes it a lot more obvious how many carbons, and because the lines, once they get too round, it's hard to tell how many carbons there are, especially if you're drawing it by hand. This can make cis or trans, and it's nice because you can see the difference between the cis and the trans very easily, the way we drew it this way, the way I drew it this way, I guess. So it's possible to make both of these. The major product here is the cis, which follows Zaitse's rule. Right? It follows Zaitse's rule because cis is more stable than trans when you're in a ring. Okay, no problem. So Zaitse's rule is followed whenever you have small alkoxides. But what happens when you have bulky alkoxides? There's a different rule, of course. Bulky alkoxides have a very difficult time pulling off beta hydrogens that are blocked up, that are, there's a lot going on there, that there's lots of substitution. Because they're big and bulky, they have a hard time getting into small places. And so what they do instead, if you have a bulky alkoxide, it will pick off the hydrogens that are most exposed, which are typically gives you the least substituted product. So in this example, right, we have a tertiary alkyl halide. You could make the tetra, or you could make the gem di product. The major product here is the gem di, and not the more stable minor product. So that rule flips when you use a bulky alkoxide. And I'll show you why that is the case. This is an exaggerated redrawing of the exact same molecule. The alpha and the beta carbons are indicated, and we have the green beta hydrogen, or we have the blue beta hydrogens, and there's 6 of them. The bulky base that's coming in here kind of has all this stuff around it, right? All those CH3s. And what happens is this hydrogen, the green one, is difficult for that big bulky thing to get in that space and access. The blue ones are just hanging out right for the picking, the low-hanging fruit. It can easily get at those. So if it gets at one of the blue ones, right, you're going to have a product that looks like this. But to get at the green one, that would give you the better product, the more stable product. But just because of the bulkiness here, it has a hard time getting in there doing that. So small bases will give you the more stable product. Bulky bases will give you the less stable product. It's called Hoffman's rule. Okay. Last wrench, I promise, in this whole unit. Something weird happens when you're on cyclohexanes. These are 2 stereoisomers of, like the cis and trans isomers of 4 terp-butyl bromo cyclohexane. Both with a small alkoxide or large alkoxide will undergo E2 elimination to give you the same product. The cis is 500 times faster than the trans. So in practical terms, if the top one, you set the reaction up and it went overnight, it was done in the morning, the other one would take 1.5 years. Big difference, practically. Why is this? There's something going on. There's something specific about E2s that we haven't really discovered or talked about yet. And I'm going to come back to this just for a second to tell you what has to happen. For E2, let's say you have a leaving group and you have a structure that looks like this. When a base comes and removes a beta hydrogen, it can only remove beta hydrogens that are positioned anti to the leaving group. Right? So remember when we did Newman projections? A Newman projection of this molecule might look like this. We didn't just teach Newman projections for fun. Coming back to them. No, I shouldn't say we didn't only teach them because they're fun, because they are fun. So this carbon is alpha, this big one is the beta. We have 3 beta hydrogens. Only the anti one can react. Only the anti one. So this is the hydrogen that's going to react. The reason why the anti one is the only one that goes is because if you draw the reaction orbitals that are going on here, these are sp3 orbitals on each of those carbons. One's bonded to the hydrogen that's anti, one's bonded to the bromine, p orbital. In the product, which is an alkene, what you have is a p orbital. So what happens going from starting material to product is the sp3 orbital converts into a p orbital. So you could imagine sort of a halfway point where they're kind of starting to form, and this is starting to get long with the Br. Bromine is starting to leave. So as this reaction takes place, this would be like the transition state. The sp3 orbitals convert into p orbitals, and they have to be lined up to do that. If they're crooked, they can't make a double bond like you see here. They have to overlap at all stages in this reaction. Starting material, transition state, product. So what we get is that the only hydrogens that can react are the ones that are lined up anti, because those orbitals are lined up to make those p orbitals that will form the carbon-carbon double bond, pi bond. So we say that the hydrogen and the leaving group have to be anti-coplanar. Coplanar means they're in the same plane. Anti means they're positioned 180 degrees from each other. That's a requirement for E2 that we haven't really worried about yet. And why haven't we worried about it yet? Because all the examples I've carefully selected to show you, there's free rotation. If it's not anti, a simple rotation can take place that makes it anti. Reaction goes, no problem. But in rings, you don't have free rotation anymore. In rings, what happens is if you make a model kit and you try to build a ring and you try to start rotating carbon-carbon bonds, it doesn't work because you can't rotate it around without wrecking the other half of the molecule. So in the cyclohexane ring, we have very restricted rotation. We have two forms, right? You can flip it to the different chair forms. That's all you can do. So what happens? Let's take the cis 1-bromo cyclohexane 4-tert-butyl. Tert-butyl is a big group, right? When we see tert-butyl, we've seen it a number of times, we think size. It's big. There's two possible ring-flipped forms for this molecule, which are drawn here, which you can all draw very well since you've learned how to do this in Unit 4. Which of these is more stable?
The first one.
First one is going to be more stable because the huge group is equatorial. T-butyl, gigantic. All right, so for this molecule, we would say like 99.9% of the time it's in this conformation, 0.1%. I mean, I'm making these numbers up, but almost all the time it's in the more stable conformation. T-butyl groups super want to be equatorial. So what happens when this bromine is axial like this, that's actually the ideal orientation for bromine to be in if you want to do elimination. And that's because there's a hydrogen here and a hydrogen here that are beta that are anti-coplanar. So by putting the ring in that conformation, you're having the bromine axial, which it needs to be, and the two beta hydrogens are also axial. They're anti-coplanar, perfect orientation for an E2. And you get your product. Easy peasy. So that T-butyl group kind of locks the molecule in that reactive conformation. This one is not reactive because the bromine is equatorial, the anticoplanar groups are like CC bonds, right? So those are the anti-bonds. There's no hydrogens there, they're carbons. You can't do elimination. You can't do E2 when the leaving group is equatorial, only when it's axial. But that's okay for this molecule because it's almost always axial because that tubular group locks it in that conformation. The other one, the trans, has these two forms. What's the favored conformation here? Left or right? Yeah, left, big time. This is the favored conformation. Both equatorial. So yeah, like 99.999% of the time it's like that. Basically never like this. Sometimes, but not very much. In that more stable form on the left, can that do E2? No. Can't do E2 because the bromine is equatorial. It has to be axial. It can do E2 like this, but it's almost never in that form. But it gets in that form, if the base is in the right place, if everything happens just right, it can do E2. So eventually, this molecule is flipping back and forth to some extent. Over time, eventually, enough molecules will end up in the right conformation with a base there that it can do E2. But it's going to be slow. It's going to be a slow reaction. And that explains why that cis isomer reacts so much faster than the trans isomer. Trans, most of the time, puts the leaving group in the unreactive equatorial position, whereas the cis, almost all the time, puts the reactive leaving group in the reactive position, which is axial. Yeah, we had talked about this. So this is a general thing in cyclohexanes. Only axial leaving groups can do E2s, and only if there's also anticoplanar hydrogens, axial anticoplanar hydrogens. Imagine an example like this. Those are CH3s. If I was to give you this molecule in the midterm and say, put this in a chair conformation, I'm sure you'd all be very comfortable with that. We could do that. Let's do it. And let's say this is carbon 1. Bromine is up. On carbon 2 and carbon 6. Carbon 2, the methyl is down. Carbon 6, the methyl is down. Don't like how I drew that. Let's draw it like that. And it's got a hydrogen here and a hydrogen here. Can this one do E2? Does it have any beta hydrogens? Yeah. It's got this one and this one, right? These are beta. But they're in the wrong conformation. They're not anti to the leaving group. So those ones aren't going to do E2. In the anti positions, we got methyls. Methyls are no good there. We need hydrogens. Well, we know if you do a ring flip, you switch. So we can make those hydrogens axial by doing a ring flip. So if we ring flip this thing, make that, then the bromine over here is in this position. The hydrogens on the beta carbons are now axial, which is good, but the bromine is equatorial. You can't win with this structure. A molecule like that will not do E2. And here's an easy way to remember it. The bromine and the hydrogen have to be trans. You could draw the rings like I have and so on, and that explains why they have to be trans. But you know, if you have a cyclohexane ring and you have a leaving group on there, like Cl or something like that, The hydrogen that you remove on the beta carbon has to be anti to the leaving group. So if you have a methyl in that position, that's fine, but not if it's anti. Same thing, if you have a molecule that looks like this, and you look at that beta hydrogen and say, well, that's not trans, it can still do E2, but it has to go to the other side, because the other side does have a hydrogen. So this could react with a small alkoxide and make this. Has to go to the other beta hydrogen, which does have a trans hydrogen there. So I swear, this is the last wrench I'm throwing in. Your job is to take all these little pieces and absorb them, and then figure out, given a set of conditions, given a structure of a molecule, how to proceed. So your first question, when you look at it, is this an alcohol or an alkyl halide? It's an alcohol, you need a strong acid. We're going to do something from unit 7. If it's an alkyl halide, we have 4 sets of conditions we're going to use from chapter 6. So for the alcohol, let's say it's an alcohol that we're starting with. We use this to determine what the mechanism is. If it's E1 or SN1 for the alcohol, start drawing it. We're going to protonate our alcohol. We're going to lose the leaving group. We're going to make a carbocation. Then we're going to stop and think, can this rearrange? If it's secondary, it can rearrange. Not if it's tertiary. Make the carbocation, rearrange it if necessary, and then check, is the acid that we used HX, in which case it's substitution, or was it sulfuric acid, in which case it's elimination? If it was a primary or a methyl, then we're going to do E2. We're not going to make a carbocation. We're not going to have rearrangements, and that's it. The alcohols are so much simpler because we don't have to worry about this anticoplanar business for primary and secondary. Sorry, for primary, for alcohols, because primaries, it's always the same. You can't have a primary carbon on a cyclohexane ring. Have it coming off, but it's part of the ring. You can't have that. So it's everything's basic. It's simpler for the alcohols, the exception of the proton transfer step, which is the same in every case. So if at the beginning it wasn't an alcohol, it was an alkyl halide, we have to determine, is it primary, methyl, secondary, tertiary? What are the conditions? Bulky alkoxide, small alkoxide, strong nucleophile, protic solvent. Use that chart to figure out what the mechanism is. If it's SN2, we have to think about inversions. If it's E2, we have to think about anticoplanar if you're on a ring. If it's SN1 or E1, you have to think about rearrangements. And if it's, what was the other case? Left, oh yeah, bulky or small, is it Hoffman or Zaitsev elimination? That's not too much, is it? There's no better feeling in this world than when you've got this all figured out. And it's like, well, that might be overstating this a little bit, but if you can keep all of those things straight, and right now where you guys are at, you're right at the beginning of all this. And it's like you're at the beach and a giant wave comes and knocks you over. And everyone's on the ground now picking themselves up. But eventually, it's fun to play in the waves, right? Once you know how to do this stuff. It's great. What else do we have here? Anticoplanar, we talked about this. Dehydrohalogenation, we talked about. to death in the previous chapter. The only difference is, yeah, there's nothing new here. The only thing that's new, which we're not going to do right now, is some alkyne chemistry. Related because we're making multiple bonds, but it's separate from everything else we've done in the last 2 units. Maybe we can deal with this on Monday. But we're going to do practice on Monday. We're going to have, wait for emails to come. Emails are coming, and we'll have a bunch of information for you about the midterm. Mostly the same as what you've seen for the last one as well. All right, thank you, everybody. I'll post this as soon as I can, and I'll be in touch.